Hello, this is Andrei, and today we are discussing that neural architecture search evaluation is frustratingly hard. This paper was published at ICLR 2020 by Antoine Yang, Pedro Esperanza, and Fabio Marlia Carlucci. Now, they argue that the current neural architecture search, commonly called just NAS, it's a promising new research area, but the current research has two main problems. The first one is that they have call it poor standards for reproducibility, and this does not allow researchers to understand when, if, and especially why specific methods work. And the second problem is that in this search space in which new models are searched, the actual searching method does not influence much the result, and the actual search space, which is humanly defined, has a much more influence, and this is a problem that they argue in this paper. But as any good paper, the abstract tells most of the story, so let's start with the abstract. And then let's move to the experiments and draw some insights and some conclusion. Now, we see that neural architecture search is an exciting new field which promises to be as much as a game changer at CNNs in 2020. Let's take a step back. What is this neural architecture search? And essentially, currently we use standard architectures. We have, for example, a ResNet, or we have a VGG, or we have excite and squeeze networks, or we have all these architectures which were essentially made by trial and error by humans, and they work well. But in the holy grail of machine learning, like the ideal case is that these things we do not have to trial and error, and we have an algorithm which does that. So this neural architecture search area essentially tries to automate the process of finding architectures, good architectures. And the way that it works is that you define basically a few operations. No, actually, let's take a step back. Imagine that this is the search space of all possible architectures. So here are all possible architectures. Now we already know that call it a standard architectures like a ResNet, a VGG. We know some things which worked in the past. We know that we have this residual connection. We know that the filter size should be, let's say, 3 by 3, and we know from the 2014 ICLR challenge that let's say if you have 9 by 9 filters are wrong. So we have prior knowledge. So with this prior knowledge, then researchers consider, firstly, this huge space of all possible architecture is like gigantic, so it's impossible to search through it. So they decided, hey, this is the search that we should search. Because in this search space, we essentially bias the search through a space where we think it's highly likely to find an architecture. So in here we have, things like 3 by 3 filters. We have, the residual connections. We know things which already work. Here, for example, we have 11 by 11 filters. We already know it not work, so we shouldn't waste the time here searching. But now this paper argues that, hey, this space that we currently search for, it's firstly too small. Like, there is not enough variation in there to make big differences. So first, they are going to argue that in a way we should make the space bigger because we want to search for new things. But if we limit the space to the things which we know already work, then this is going to be a problem. But the whole point of architecture search is that you essentially search a possible architecture. And you don't do that like completely from random. You define a set of operations which you already know to be working, and essentially this neural architecture search is essentially, hey, find like the best combination of these things, like put two layers of convolution, then put a max pooling, put another max pooling, for example, put more convolutions. This is what we want. Essentially, we want the order of the of these operations, where the operations are already defined. But let's continue this thing, right? So despite many great works with substantial improvement of this task, comparing between methods is still very much an open issue. We start getting a sense of what's the problem. While most architectures are tested on the same data set, you can imagine this is going to be a problem. There is no shared experimental protocol followed by all. As such, and due to the underuse of ablation studies, right, there is a lack of clarity why certain methods are more effective than others. So they make several contributions. Firstly, they do like large-scale experiments where they test multiple methods on multiple data sets, and they are going to draw some insights from this thing. They are going to propose something very interesting, is that people typically report the best accuracy of the method of the architecture that they find winning using NAS, but that's going to be a problem. So to overcome the hurdle of comparing methods with different search spaces, we propose using a method that relative improvement over randomly sampled average architectures. So this is as follows. Hey, I think it's time to clean a bit here. Good. So we were having this space where we were actively looking for things. And now we are looking to find the best, meaning this is, let's say, the maximum, like the optimal in this thing. But the question become, hey, how much is, this maximum different than this space? Like maybe anything from this space would be good enough. The answer is that yes, they are going to find that anything in this space is already good enough. So how do you find that? You just pick random architectures from the space, and you get the accuracy, and you compare that with the max one, and the max one is essentially almost no improvement to this randomly picked architectures. So surprisingly, we find that many techniques struggle to significantly beat an average architecture baseline. Average architecture means like you random architectures from there. Think of it like that. We perform further experiments with the commonly used dark search space in order to understand. These experiments highlight that, they highlight three interesting things. The use of tricks in the evaluation protocol has a predominant impact on the reported performance. So, tricks in the evaluation protocol. There are multiple tricks, meaning auto-augment, for example, meaning how to find the best data augmentation, which they slightly make a difference. So different papers use different, in this case, data augmentation techniques, which makes it hard to understand whether is the training procedure better or is just, you find better architectures. It's unclear. The cell-based search space has a very narrow accuracy range, such that the seed has a considerable impact. What is this cell-based search space? Interesting question. So we know that, let's say this is a CNN, right? So the CNN goes like this. This whole thing is the whole architecture. And a cell is essentially imagined as that it is one layer, meaning it can be one layer, but typically it has two things. It's something, I think it's called like a normal thing, and it's called a reduction. In the most basic case, a reduction is like a max pooling. This is what we use. and a normal can be, for example, just a CNN layer. It's normal because it maintains the dimensionality of the input and the dimensionality of the output, while this one reduces the dimensionality of the output. Now, in other architectures such as Inception, this, call it block, meaning a cell, let's use the term cell, it's not just one CNN, it's something like more complicated, meaning you have the input and it goes through several, like CNNs, like several convolution blocks, and then it concats and so on. And the point is, like, here you can use, for example, a 3x3 convolutions, maybe here you use a 5x5 convolution, maybe a 7x7, maybe another 3x3. This entire thing is a cell. And the operations inside the cell are this thing, 3x3, 5x5. So they're saying that most NAS algorithms focus on essentially creating these cells, essentially these layers. And that's essentially wrong, because we look too closely to, like, there is not much things you can change into such cells. Like, they are already essentially not overfitted, but they are essentially, or like, it's a fixed problem. There is not much space for improvement here. So they're going to argue that, hey, instead of looking at the cells, which it's call it a solved problem, the research should look at the overall architecture, like, hey, create new things in the whole architecture, like create the residual connection, like the resonance, or create something new in the architecture, because that's the place where the performance boost is going to come from. So also, the hand design macrostructure is more important than the searched microstructure. We are just talking now about the cells, and it says that the hand design macrostructure, so this hand design cells, is more important than the searched microstructure. Essentially, these operations that we discussed, like the convolutions, there is not going to be much difference there. The first point is that the depth gap is a real phenomenon evidenced by the change in ranking. So the other thing is the depth gap, meaning you have an architecture, but it has a number of layers. And the question is, how many layers should you put? It's a good question. And the point is, the more layers you put, the different results you're going to get. And this is another place where methods should be more aligned on using such things. So in the end, they suggest best practices that hope to be useful for the community. As a quick overview, recent research has proceeded at a rapid pace, and there are many search strategies. There is things called using reinforcement learning. People use evolutionary algorithms. People use gradient-based methods. So there are many ways in which you can search for such an architecture in a search space. So now, these methods have been typically decomposed into three components. This is key. The first one is the search space that we discussed. The other one is a search strategy, meaning you have the space. The other one is like, hey, how do you move through this space to find the best architecture? And the other one is the model evaluation strategy. Essentially, how do you evaluate one of this? Like, how do you train? What's essentially the training procedure plus the metric? Training procedure, like what's the data augmentation, what's the optimizer, what's the learning rate, things of that, and the metric is what they use. People typically use accuracy as a metric. But now, their findings suggest that most of the gains in accuracy and research contributions to NAS, which is orders of like 1 to 3-4%, have come from manual improvements in the training protocol and not from the search algorithms. the key point that we get even from NAS, meaning neural architecture search, is that we want a good search algorithms. Like we hypothesize that we search for architectures, but in reality what they tell us is that, hey, in this search space that we look, anything that you pick is good enough. Like there is no need to search much, because the space is that small that even if you pick anything from it, it's gonna be good enough, which is sad in a way. Let's look over some experiments that are going to shed some light over this thing. Okay, so let's look over here. The first thing they do is that they compare the search methods and random sampling from the respective search space. Random sampling means you just pick essentially architectures, you sample an architecture from this search space, so you get a random architecture, and you compare essentially the one which your search algorithm finds, which is the one that is sampled at random. Now, this is the same graph, but it is on 5 datasets. Now, let's understand what are the axes. The first one is random sampling, so the accuracy of a randomly sampled architecture. And on the y-axis, we have the search method, meaning the accuracy of the search-based found architecture. And notice that this line essentially means that they are equal. You see, it's 94, 94. It's 96, 96. So this means that a randomly sampled is as good as the search architecture. In the ideal case scenario, this is the corner that we want. So we want, ideally, that, let's say, the search architecture finds something that is significantly better than the random sampling. Because if not, I mean, searching in this spaces costs like 4 days. So why would you spend 4 days when you can just random sample? You would not. So ideally, you want to shoot to that corner. And you notice something to also mention is that most of these papers in NAS typically, like you are getting your architecture from this space, and you need to assess which one is better. So you need to train them and get the accuracy. But typically, meaning almost all of them, test on cipher 10. Like you train architectures on cipher 10 to decide which one is better. One thing which they propose is that, hey, people should test, meaning train and decide on the search method on multiple datasets. So here we test on 5 different datasets. Now there are multiple methods which they are uses, and I have to acknowledge that this one called Manas is made by them, but by the same people. Notice essentially that this line shows that a searched method is as good as a random sample method on this dataset on Cipher. Like in some cases it's even wrong, but in most cases slightly better, which I would call it's the same, right? So for this thing you pay 4 days, not good. Cipher 10, almost essentially things. Like the difference between things is like 2%. It's still an improvement, I'm not saying that, but it's not what one would expect when you spend that much compute. Here, essentially again, like 2%, like 2%. So the clear idea here is that a random architecture from the space gets essentially the same result as a NAS-found architecture, which is very interesting. But I would argue something. I didn't say it in the paper, but I think it's important to notice that all those tasks are very simple. Like you get on Cipher 10 97% like with a random architecture. Not to even mention not to even mention that this search space, which is essentially human defined, was already essentially fine-tuned to work well on Cypher. Like, people were testing and finding architectures for the past 7 years on Cypher and ImageNet, so the search space is already fine-tuned to work well, not to even say that the Cypher is an easy task. So I would argue that a problem is that all these datasets are too simple. And I understand that the dataset needs to be small, such as it trains quickly because you have many of such architectures. But I would argue that one could, for example, train on, I don't know, like 25% of Cypher. Like, just train on very little data to see how well it generalizes. You don't want to be in the boundary of 97% accuracy anyways, because, I mean, what can one improve? 3%? And to get to 100%, it's already like, it's not reality. So they argue that one should test on multiple datasets. I would also add that one should just not use such simple datasets. Like, I understand it's hard to get more data, but maybe you can just train on half of this data. So from now, we got the idea that a random architecture from this search space is essentially as good. Let's look at other things, and this is essentially a plot which shows these are the methods, and this is the top test one accuracy. Notice that we have the random sampling, the method, and the cost. I mean, just look at this thing, NAS-found. Like, it costs 4 days in GPU, and it's not like it costs 4 days, and the search method is even worse than a random sampling. Like, and for the best ones, for example, this one's, Darts is a famous one, you get like 0.5. Something's not cool there. Let's look at some more results that they do. So first thing, we argue that the search space is already too restricted and it's going to be something good enough. The other thing which they argue in this thing is that the training matters as well when they compare results in the papers. So it's a comparison of different augmentation protocol for the Dart search space. So there are different, augmentation methods in order to how to look into the space, but also how to train. So for example, this auto augment is a method to essentially augment the data, and all these are like very small things. It's like change the data augmentation and call them tricks. These are tricks, but you notice that when you use all the tricks, you essentially get 3% more performance than when you do not use any trick. And the key point is that different papers use different tricks, so it's call it impossible to understand whether the trick got you better results or the way you search through this space got you better results, which is unclear. So they argue that let's all just use either all, either none, but the point is, let's set up on a common way of measuring these things that is shared across the community. Another thing, which is, I think, very interesting, these are the training curves for the 200 randomly sampled architectures. So I think it's on Cypher, to be frank with you. I mean, yeah, like it gets already like 90-something% accuracy, but here are 200 sample architectures. So notice that by itself, essentially all the architectures are the same. Like, however many you sample, they are essentially the same performance, and this again leads the search space, it's too small. Now other things which they are doing, let's look at this figure 8. They have plenty and very good ablation tests, but the conclusion is that we should make the search space bigger. Changes in the ranking of different architectures when trained with two different seeds. So in here, they do literally nothing other than changing the random seed. And look at how much this, like the ranking between multiple architectures when trained change. I mean, notice that the ones which were highest are still highest, but there is too much change because of just changing the seeds. And they argue at some point that essentially this change is not like the results change much. It changes the ranking but not in the absolute value. So everything is like 97% plus minus, I don't know, there is something like 0.3% variance. So the point is that the search space is that biased that anything you get 90%. So now by the ranking is given by this small variance, which is something like 0.3%, which is small. So the ranking is meaningless because anything is that close, that noise just makes them better than the other one. So, even a random seed can change the result. They argue, hey, people, just tell us the random seeds in the papers, because without telling us the random seed, then we can't know. I mean, we just can't reproduce your results. Yes. And in the end, they come out with some best practices from all these observations. The first one is that augmentation tricks. We suggest that both results, without and without training trees, should be reported. They make a nice shout out. So essentially, this graph, they're saying, hey, use your architecture search with like just normal base training. Don't use any tricks. We want to know how good it works without any tricks. And then also other tricks, because we are curious for that, but we want to know essentially the actual truth, like how well does that go. The search space, and this is a good one. As our findings suggest, the overall wiring, the macrostructure, is an extremely influential component in the final performance. They essentially say that the macrostructure, meaning like, for example, the depth of the architecture and the architecture itself, is much more important than small changes in the cells. So future research could investigate optimal wiring at a global level, right? Essentially find new architectures. We discussed that they suggest that this ranking should be done on multiple datasets at once rather than on CIFAR. I would go as far as saying maybe people should stop using CIFAR for such things, because it's too easy things. It's a too easy data set to allow large variance to be able to distinguish clearly between architectures. Investigate hidden components. So they suggest that proper ablation studies can lead to better understanding of contribution of these such things in the pipeline. So typically when a new NAS method comes, they come up with a new search space, they come up with a new way to move into this search space. And they say just ablate how much does the space influence things, ablate how much does the search, ablate how much does the training method influence, such that people know that. And of course they argue the importance of interpretability, and with the hyperparameter tuning, these methods, they have some hyperparameters as well, and they argue that it's costly, sure. So the hyperparameters that are general enough so that do not require tuning for further tasks, or the cost is included in the search budget. So they're saying that for future researchers, like, hey, first, like, tell us what hyperparameters you use, or essentially tells us the cost in the search budget, or just make hyperparameters which work in general. They're saying, hey, make it as easy to continue this research, essentially. But yeah, this is a very interesting paper, and I would go as far as saying that maybe they make a shout out to the community as, hey, this is an exciting field, let's continue to move in this direction, but we need all to set on a set of standards that allow us to understand why things work better and if things work better. This is all I had. If you enjoyed this channel and you would like to get more paper reviews, I am going to start pumping up content. So thank you for watching, and make sure you subscribe and you like this video. See you in the next one.